everyone, and welcome to the Joy of Abstraction Book Club, Chapter 12. Oh no, I've got the captions showing and that's distracting. Okay, I've turned them off. It's great to see you. Thanks for being here, and thank you again to the Topos Institute for hosting our book club. I'm really glad that there are so many questions coming in, and they're quite profound. They're quite tough questions, so I'll see what I can do to get my head around answering them. This chapter was about the category of sets and functions. And the first question is set another example of dimension shift? Great question. When I say dimension shift, I probably ought to stress that that is not something rigorously defined. And the way, I suppose other people may use it in different ways, but the way I use it is that I'm thinking about a structure with a certain number of dimensions, but because the bottom dimensions are trivial, I can ignore them and then perform a dimension shift to shift so that I'm actually only paying attention to the non-trivial dimensions. With set, that's not really what's going on. I think that the elements of a set are the bottom dimension, and it's the upper dimensions that are trivial when we regard them as a category. So if we regard something as a higher dimensional structure by taking the top dimensions of trivial, I would not call that a dimension shift because we haven't shifted. The bottom dimensions are still the bottom dimensions. It's when the bottom dimensions are trivial, so we shift our attention up, that I would call that a dimension shift. The next question is interesting. I'm noticing the category of sets doesn't seem to tell us everything there is to know about sets, like the fact that you can take the union of two sets. I'm curious, and so now this is me answering the question. I'm curious as to why this person asking the question thinks that the category doesn't tell us everything there is to know about sets. Now, in this chapter, and so far, we've only done the objects and morphisms of sets. And it's true that just defining the objects and morphisms of a set, of a category, do not, oh my goodness, my grammar's gone wrong. Just defining the objects and morphisms is only the starting point for looking at what's going on in the set, the category. Deep breaths, we'll get our words in the right place. Let me try that sentence again. Just defining the objects and morphisms of a category is only the starting point for us investigating what is going on in that category. And so then when we get to the next part of the book, which is about doing category theory, that consists of looking for other features in the category that tell us more things about what's going on. And so we use the objects and the morphisms to tell us all sorts of things by looking at how they interact with each other. So we can use the objects and the morphisms of the category of sets to indeed tell us how to tell us about taking unions of sets. And we'll see that in the chapter on products and co-products, which is, well, it's the third chapter on universal properties. I mean, not products and co-products, pullbacks and pushouts, chapter 19. So we will get there because taking a union is a push out in the category of sets. So we'll see that disjoint unions are co-products and intersections are pullbacks and unions are pushouts. And so we can do all those constructions. And we'll come back to this a bit later on in this video because several people asked about what it means for the category of sets to be well behaved. And basically, it's a good question because what we're looking for is we're looking to encapsulate everything we can do with sets. We're trying to encapsulate that in the category of sets and functions. And I think that that is a largely very successful program that has happened. And so then the rest of that question said, does this mean that the category of sets is really about functions? Or does it mean that the ability to take the union of two sets isn't really a fact about sets? So the category of sets is based on functions, but the great thing about it is that it turns out if you focus your attention on functions, you can get everything you want out of the category of sets. And that's kind of the point of the starting point of category theory. It sounds like sets are about elements, And in classical set theory, sets are all about elements, but it turns out that you can do it all using functions instead. And so a way you can translate between the approach using elements and the approach using functions is that if you've got elements, you can make functions. And if you've ever done any classical set theory, you may remember that it's a bit arduous. You have to do it using ordered pairs. But if you've got functions, you could get sets back out again, because an element of a set can be located by taking a function from the one element set into your set. So if you have a set X and you want to know what all its elements are, but you're only talking about functions, you take a one element set and you look at every function from the one element set into X. And each one of those functions will pick out one element of X. And that's how you can get all your elements back, but only by talking about functions. Okay, the next question. Is there a name for categories of categories that preserve the same structure as you scale up, like posets of posets of posets? I don't know. I suppose I would call them fractal somehow, but I don't know how widespread, how many times you can really scale those up. How many things there are that you can scale up a lot. And I had a little quick Google and didn't find anything much. Perhaps there is something I don't know about. Next question. How does set theory stand today in light of the category of sets? Can we think of category theory as working together with set theory? If not, why not? I would say that category theory is more an alternate approach to doing set theory. And it's more like an alternate approach to foundations, where we take the point of view that functions are the more natural basic concept, rather than thinking about elements all the time. And I think that that point of view comes from the fact that when we're doing mathematics in other fields, it's often the maps between things that are really important, not necessarily just the elements of the things. It's how the maps work. And so I would say it's an alternate point of view. That's how I think of it. I will admit the next question is confusing me a bit, but I'll try. There seems to be a one-to-one correspondence between objects and arrows of a category and elements of a set and functions. Are the two frameworks equivalent? I think there's a type error here, because functions go between sets. They don't go between elements of a set, although I've drawn some diagrams where they map individual elements to individual elements. Fundamentally, a function goes from a set to a set. And so the objects and arrows of a category shouldn't correspond to elements of a set and functions. They should correspond to sets and functions, but they're a generalization of it. And so I don't know which two frameworks are being proposed here, because they don't really match up. So I would say no, the two frameworks are not equivalent. Does there exist a category that is not definable in terms of elements of sets and functions? Yes. So, for example, you can have a category where the objects form a set, but the morphisms don't have to be functions. So, for example, they can be assertions, or they could be matrices, or they could be symmetries. So I think that there is some confusion going on here. Well, I think what it's fair to say is that objects and arrows of a category are very reminiscent of sets and functions, and that's because they're a generalization of them, but they include many more examples. And I'm wondering if the question is, are all categories, do they all have objects which are sets with extra structure and morphisms which are functions preserving that extra structure? And the answer is still no to that. Okay, some more specific questions. Page 139. There's a couple of questions about the asymmetry of functions between inputs and outputs. So the first question says, how should I think about this being helpful? Well, so this is about the fact that when you're doing functions, there's an asymmetry between the inputs and the outputs. So every input has to go somewhere, but not every output has to come from somewhere. And also, two inputs can go to the same place, but two outputs can't come from the same place. And the reason that this definition is helpful is that it encapsulates really a lot of very ubiquitous examples. There are so many examples that behave like this. And I guess the point is, there's always a trade-off between the demands you place on a structure and then how tractable it is afterwards. So if you allow more things to count as functions, then what happens is that the structure you get out of that is a lot more complicated. And so you can do that, but you'd better really want those extra examples to be there, otherwise it's not worth it, right? If you I'm just trying to think of an analogy. So, well, it's kind of like the fact that I just bought a water rower, and it's great, and water rowers became much less expensive recently, but I think the reason is that they've made them for domestic use, whereas previously they assumed that they were only for gyms. And if it's going to be used in a gym, then it's got to be a lot sturdier and take a lot more battering than one that's just being used at home. For a start, one that's being used at home is unlikely to be used for more than a couple of hours a day, but one that's being used at a gym may be used for hours and hours every day. And so the thing is that unless you really want that extra usage, there's really no point spending the money on a fancier machine. And that's the point of definitions in mathematics as well. Unless you really, really need to be able to do those extra things, there's no point spending your resources on them. And in this case, resources don't mean money, it means technical effort. So allowing more things to count as functions is so much more technical effort. And in so many cases, you don't need it. And so it's really not worth it. Now, the next question is there a name for the maps more general than function, which admits sources without targets and sources with more than one target? And the answer is yes. So if you want to allow inputs that have no output, those are called partial functions. And if you want to allow sources with more than one target, those are called relations, because a relation between two sets is just a set of pairs saying which ones are related. So if you've done classical set theory, you know that in set theory, a function from a set A to a set B has to be defined in terms of ordered pairs, one from this set and one from that set. And then you have to put a bunch of conditions on, declaring when it counts as a function, which is essentially when every input has an output and no input has more than one output. There is a category of sets and partial functions. It's just a lot harder to work with than the category of sets. And similarly, there is a category of sets and relations, and it's very important actually, but it's also a lot harder to work with than the category of sets and functions. And so if you can do it with sets and ordinary functions, it's just better to do that, because there's no point making all that extra technical effort unless you really need to. That's what the point is. So I suppose another moral of this story is that it can seem that abstract math is about making things as general as possible, but it really isn't. It's about finding a generality that is illuminating for what we're trying to do. And if you just make things as general as possible, then you can make so many technical complications for no reward that it wasn't worth it. Okay. So How would I represent that bold set in handwriting? Oh, thank you. That's a much easier question for me to answer. We do it with an underline. So just write set and underline it. And here we have a definition of sets in terms of categories. Is there a definition of categories in terms of sets? Yes. If I understand what you mean, I would say yes, as long as the categories are small, which means that everything involved is a set. And I think that this definition is in here under alternate definition of category somewhere. I should probably have looked this up before starting to make this video. Let me see if I can quickly find it. Okay, I think that there is a definition of category in terms of sets in section 17.5, which is the chapter on duals, at the end of the chapter of duals. So you can make it via a set of morphisms and a set of objects and some functions between them. So that's on page 235 if you want to jump ahead and look for that. And so finally, a couple of questions from page 145 about well-behaved. So just to recap, what I said on page 145 is this category, the category of sets and functions, is not only the starting point for building many other categories, it is also the prototype for a well-behaved category. And so the question is, what's the meaning of well-behaved? What is the distinction between well-behaved and not so well-behaved? Are the latter of any interest? Again, this is something that's an idea rather than something rigorous, but the idea is sort of that the definition of well-behaved is that it behaves like the category of sets. Because what we found in the course of doing mathematics is that you can do a lot with sets and functions. There are loads of constructions you can make, as the other question asker asked. You can take unions, you can take products, you can take disjoint unions, you can do all sorts of constructions and things work. There are loads of techniques that have been built up, and all those things are possible and nothing goes wrong. So that's a good, it has turned out to be a productive context in which to do mathematics. And so that's, in a way, the definition of what well-behaved means. It means, do things work well enough that we can function? And it's a bit like the Earth, the planet Earth that we live on. We could take this as a prototype for a well-behaved planet in the sense of it's conducive for life. And then we can look around in it and see what makes it conducive for life. So the category of sets and functions is a very conducive place for mathematical life. And then we can look in it and see what makes it conducive, so that we can then look for those features when we go to other worlds to see if that other world, we can still do mathematics in that other world, just like we go and look for water on other planets to see whether life might be feasible there. So the not so well-behaved ones are of great interest, because very few places are quite as well-behaved as the category of sets, but we can look for features to see what we still can do. So sometimes we can't necessarily take all products, for example, but we can take some. And actually, there are some people who think that we should be able to do more things than the category of sets for things to be well behaved, and that everything should be able to live in the category of abelian groups or something. So it's pretty subjective. I mean, just like different people have a different idea of what it means for children to be well behaved. And so depending on what kind of mathematics people are interested in doing, some people take as a baseline that you always have a certain amount of structure around, and other people don't. So, but the idea to get from this notion of well-behaved is can we do the things that we want to do, and figuring out what makes that happen is something that category theory is very good for. Because if you just figure it out in terms of elements of sets, you can't immediately transfer it to another category. Whereas if you figure it out in terms of sets and functions, then that's just morphisms in a category. So as long as once you've figured out what those morphisms the structures that they need to have, you can just look for those structures immediately in another category. And that is the principle of expressing something categorically. That is only using the morphism structure. So an example of that is when we look at isomorphisms in the category of sets, we'll see that a function has an inverse if and only if it is a bijection. Now, the thing is that when you say bijection, you're referring to elements in sets, because it means that every element in this set has exactly one element of this set that it goes to, and every element and so on, there's the elements exactly match up. Whereas to express that just in terms of functions, what you do is you say there's a function going that way and a function going this way, and they are inverses of each other. So that if you go around like that, you get the identity, and if you go around like that, you also get the identity. That definition in terms of inverses can now be put in any category, whereas the one about bijections can't necessarily. Or if you did just put it in there like that, you might not get the thing that you're expecting, as we may find out in the next chapter when we talk about topological spaces. So I hope that gives you some ideas, some more ideas about those things. Some praise at the end. Thank you. Reading your book is my fun time. Your title couldn't have been better chosen. Oh, thank you. And then someone else said thank you, and someone else also said thank you. So thank you, everyone. It's great to see you, although I can't see you, but it's great to pretend like I'm seeing you. And thanks again to everyone at the Topos Institute for hosting. We'll move on to chapter 13 next. Hope to see you there. Bye.